Okay, now can we start now? So what we learned a few moments ago was about this theorem, which I call it, and these are the laws. And of course, unfortunately, I missed that other law to put it here. But you know that law as well. So these are the laws. I want you to have these laws somehow in your memory so that you can use this. So that is, these are the laws of, especially the last one. So these De Morgan laws, conditional laws, contrapositive law. Yeah, this is not that important. It's of course important, but it's not very ubiquitous in logic. So these are very important ones that I want you to know about. Okay. For example, do you remember we started with one uh, example today, but we used the table to prove it. So we want here to use the algebra to prove it. Do you remember what was it? It was P if P then R, and if P then Q. We showed that this is logically equivalent to saying that, uh, was it the same? No, this is again Q, sorry. I don't know why I have this in my memory like this. So Q R, and then we showed that this is equivalent to this. I hope that I'm right, yes. So now let us see if we can prove this. We come back to this example later because might be it is a little bit more involved. Let me start with a very simpler idea. So the point is that I want to start from one side and reach to the other side just using the logical laws without referring to any table. So let me go here. For example, that you see it on the board. Let us start doing these simple ones first. Yeah. And one of them is, by the way, something similar to this is here. So let me do the first one myself. Use propositional logic laws to show this. P or, we want to show that. So P or Q and not P. I want to prove that this is equivalent with just simply saying if P or Q. Yes. So how can I do that? When you want to do this using the logical laws, it is better to start from one side which is more involved and try to simplify it using the logical laws and reach to the other side. So here, I will solve this later, okay? But let me solve the simple one here. So if I want to do that, I will write the left-hand side because the left-hand side is more involved than the right-hand side. So I decide to start from the left side. Which law is useful here? I have a disjunction and I have an injunction. Whenever this comes in, you need to think about what? Distribution. But before doing distribution, you need to think about absorption laws. Absorption is involved if one of them is exactly repeated. So here I have P, here I have Q, here I have not P. I don't have P itself, I have not P. So this is not absorption law. If it was just P, what was the answer? Just P because of the absorption law, because one of them is repeated. But now this is not repeated, so this means definitely it is distribution. So how should I distribute this? I would say P or Q and P or not P. Is that understandable how I'm writing it? Yes? But is there any other law involved here? For P or Q, I cannot write anything specific, so let me copy and paste it. But is there something I can write for P or not P? The door is open or the door is closed. This sentence is always true, yes? So this is a tautology, regardless of the value of P. And that is one of the formulas in my list. So I can copy and paste this and instead of this one, I just simply write a tautology. Then I have another proposition, whatever it is, I don't care. but this is and a tautology. So what is the answer at the end? It is just the first one, because I just told you the tautology is the identity element of conjunction. So it doesn't have any role there. So the answer becomes simply P or Q, and that is equal to the right-hand side. That is equivalent to the right-hand side. So this way of doing it is faster and much more fun, yes, rather than doing it using the table, because table is always the case here. Okay, is that clear? Okay, so for example, let us go to the next one. So the next one is this one. I want you to do it yourself before I do it on the board. Okay, so you can do it until I write the question here on the board. Okay, should we do it? So how can I do that? Of course, this is the left side, which is more involved. So let me start with the left side. Okay, help me to do that. Which rule or law do you want to use now?
The first one, the negation of, you can just write it as P and Q.
De Morgan law, yes? So if I want to write all these steps, it becomes, this is a disjunction, and I want to negate a disjunction. According to the De Morgan law, I can negate them individually, but the price I have to pay is to transform a disjunction to a conjunction. Let us do it in our head. Negation of the first one is negation of the negation, which is P. And then this one is Q. But instead of having or, I will have and. And then I have to copy and paste the rest. So it becomes or P and not Q. Okay, is there anything I can do now? I can factorize. This pattern should be familiar to your eyes. You see I have P and here. I also have P. But let me ask you one question. Can I say this is also factorization? So let us say that I have P and Q. Again, I have and I have P and not Q. Okay. And so for example, someone writes it like this. Okay. I'm just asking you. I am saying that I write it like this because I'm saying that, okay, P and I factor P and out. My question is that, first of all, is it a distribution law or not? It's not. Because all of them are and, the same. Distribution needs two different operations. Okay? But the second question, is it valid or not? So that's important to understand. The algebra here is not exactly the algebra of numbers. So there are some counterintuitive things that you have to be careful about. First of all, you told me correctly that this is not a distribution law because all of them are ands. For distribution, I need two operations. But the second question is that, is it valid or not? And if it is not, okay, but if it is, how can I justify? I would say this is valid again. Okay, I grant this for you. But can you justify why this is true as well? Okay, so let me write it in this way. My question is that if I have A and B and A and C, can I still factor A and out and write B and C?
Yeah, but it's commutative.
Yes? Can I? Can you justify why this is also true? There is no law for it. There is no name for it. I want you to understand. It's a combination of different laws. Yes?
It's commutative, so you can group A, and that just becomes A.
Yes. First of all, I really don't need to be worried about pairs of brackets because it's associative. And because it is commutative, for example, when I take the pairs of brackets out, it is still the same expression. It is not ambiguous. If someone asks you why, you refer to the associativity. And now, between these two, I can do the commutation here. So it becomes A and B and C. And now, because it is and it is associative, I can group them in that way. Yes? And A is the idempotent law, so I can write it as A and B and C. Okay, so if I want to go from here to here, it is not factorization. It seems as if it is factorization. It doesn't matter if you want to think in that way, but that is not the real factorization because all of them are and. But how many laws I need? I need associativity, I need commutativity, I also need idempotent law. So if I combine these three laws, then this is justified. So from now on, if you understand what is how is it working, you can immediately use that. But I want you to understand this is not distribution. Can you continue more now? Q and not Q is a contradiction. So it becomes P and a contradiction. And P and a contradiction is a contradiction. Yes? So this is always a contradiction as well. But let us go back there. So I hope that you understand the difference between these two. Both of them, so this, if someone asks you if this is true or false, you would say it is true, but not because of distributivity, because of associativity, commutativity, and idempotent law. Yes? Okay, so here we continue. So what happens here? I can factor P and out. Because this is distribution, I have two different type of operations here. So what is left? Q, and what is left from there? Or not Q. Yes? So then what happens? Is there something I can write here? The door is open or the door is closed. It's a tautology. Yes? So it becomes P and a tautology. And what is P and a tautology? If P is true, T is true. If P is false, false and T is false. So in principle, it is always P. I told you, tautology is the identity element for this operation. So it is P and it is equal to the right hand side. So I was able to show this equals to that. Okay? Okay, so now I want you to think about the next one. Unfortunately, the battery here is finished and I don't have any batteries here. Do I? No. So it will affect a little bit the recording, but hopefully not that much. Anyway, I will speak a little bit louder. But I want to ask you some question here. Number 3, if I insist you to give it a name, okay, can you tell me what is it telling you? You see, I want you to understand deeply these things, yes? So if you look at number 3, we haven't proven it yet, but we will. If we do, what can I say this is telling me?
If P then Q and P then R, then P then Q or R.
No, according to the words of associativity, commutativity, distributivity, something like that. So how many operations are involved here? A conditional and a conjunction and the arrow. Now look at the right hand side. Okay, let me write this one. So here P, if P then Q and R. Is this distributive over that one? So I don't know if it is distributive. These are not the things I have it in my memory either. But I mean, let us assume that this operation, this connective, is distributive over this connective. So what, if it is true, what do you write? You would write P, if P then Q, I am distributing this over this. So this becomes P, if P then Q, and if P then R. Yes? But these are not one of those things, even I have it in my mind. But this, if we can prove that, then it guarantees that this connective is distributive over this connective. Yes? By the way, is it understandable logically? This tells you that if I grant you P, then Q and R are both granted. This is because this is the way that you look at it. This is the sufficient condition for these two. Because this is and. Okay? So it means that if you give me P, Q and R are granted. What does it mean? It means that, of course, if you give me P, Q is granted. If you give me P, R is granted as well. But let me test your intuition. What do you think about this? Do you think this distribution also works based on only intuition? If you grant me P, then either Q or R is granted. Do you think this is the same thing that if P then Q or if P then R? So that's why I'm saying that in logic it is also good to think about how intuitively you can come up with this idea. This tells you that if you grant me P, either Q or R, of course or in mathematics means either or both. So if you grant me P, either Q or R is granted. Is it the same thing as say that if you give me P, Q is granted, or if you give me P, Q is granted? Do you think they should be equivalent? Okay, for me it's also the same. We can test it later, okay, to see if our intuition works. But this is always good to have this intuition, but at the very end, what you can rely on is the calculation, it's precise calculations. Okay, but let us see if it is true or false. Can I say this is also distribution? This is also a version of distribution law? Yes or no? Is it distribution law as well?
No.
No. Why? Because I have three connectives involved. One of them is this arrow, one of them is or, and the other one is and. Yes? It was true. We proved that it is true, but it has nothing to do with distribution or something like that, because distribution is always involves with two operations, two connectives. Okay. This is what we want to prove according to the problem here. So can you help me to do that? I don't know which one is suitable. I don't know if it is better to start from the left side to go to the right side, or start from the right side, go to the left side. I prefer to go from right side because it seems a little bit more complicated, yes? So if you don't worry, if you don't mind, let me just start from the right hand side. So what can I write for the right hand side? Okay, so let me copy and paste it in front of your eyes. So it is if P then Q, and what? If P then R. Okay. Do you remember, or can you guess which rule will be important first?
I don't remember what it's called, but it's not P and Q.
Yes, that's called conditional law. So the conditional law, whenever you want to do something with this, get rid of the arrow, because we do not have that enough rules about arrow. Yes, but we have a lot of rules about disjunction and conjunction. So let us get rid of them. The first thing comes to mind. And that is one of those things that I told you that try to remember, memorize. So what can I write about this? I take this one and negate it. You remember? And I transform this into or, and then keep Q as the same. Yes? And I can do the same thing here. So it becomes not P or R. So that's possible. But then what can I do? Factor it out, distribution, yes? Or and. So I can factor not P out with which connective? With or. And what is left for me? Q and R. I hope that you don't have troubles here. Now, can I go back to a conditional? Yes, because I want you to understand that if I have a box, if box then circle is equivalent to what?
Not box.
Not box
Or circle.
or circle. Yes? Okay, let me ask you one question. If I insist you to write this as a conditional, how do you write it?
Not box, then circle.
Not, if not box, then circle. But there is also another way to do it. Not circle, then box. Yes, that's the same thing. Yes? So it doesn't matter. So you be careful. If I want to go from a conditional to a disjunction, there is only one way to do it. But if I want to go from a disjunction to a conditional, I can do it in two different ways. That they are not different, I can do it in two ways. So now I want to go from a disjunction to a conditional. Why? Because I need a conditional on the left side. Yes? So what can I write?
If P.
Yes, if P, then Q and R. Yes? Is that understandable? Because if someone asks you why, you see, give the role of box to this and give the role of the circle to this. What do you have? You have not box or circle. Not box or circle can be written as if box, then circle. If box, then circle. Yes? And that is it. So that becomes equal to the equivalent to the left hand side. Okay, let us test our intuition immediately, because intuitively we thought that this should also be true. Let us see if we can grant it or not. This is not one of the exercises that I show you on the display, but here, do you think this is correct as well? So let me start from the right hand side. So right hand side, I can just immediately write it as what? Not P or Q, or not P or R. Is it distribution or something like that here involved? No, because all of them are disjunctions now. But do you remember something like this? Do you remember? All of them was conjunction. The same is true if all of them are disjunction. You can convince yourself exactly like the way I did it here. So what can I do? I am not factoring anything out, but it looks like I am factoring not P or out. Yes? So what is left is Q or R. Okay. So now, can I write this as a conditional again? Yes. I can write what? If P, then Q or R. So our intuition was correct. So we can say that I didn't have this in my memory, but anyway, a conditional is distributive over both conjunction and disjunction. So our intuition, that's what I'm saying. Don't give up about your intuition unless it is so complicated. Yes? So this is equal to the left hand side. So yes. Now I go back here to the board. So this one is probably a little bit harder one. I want you to try to yourself first. Okay, so what about this one? Do you have any idea? Which side do you want to start with? Left side is more involved, okay? Okay, let us do it together. So you tell me what to do. The left side. What is your first what is your first reaction?
Inside the brackets, make it so it's...
Yeah, so let us keep the first one. I also have the same feeling. So let us not make things more complicated. Let us keep this one. And then, within the pair of brackets, which law you want to use? The conditional law. So the conditional law was that if I have a box, then keep circle. What can I write? I can write not circle or the box. Sorry, not the box or the circle. So, but not the box means what here? Means P. Not the box means not P, which is P. This will change to a disjunction, and then I keep the circle as it is. Do you agree? Okay. So far, so good. Okay, so do you have any other ideas what to do?
I would distribute P now over R and Q.
This one?
Yeah.
Over this and that?
Yeah.
What is the motivation behind doing that? I think it's a good idea. Because at least P or Q, which I see on the right side, appears if I do this distribution, yes? And I don't want to use that rule of distribution of conditional over disjunction. We just know that this is also true, but this is not one of those fundamental laws that I have it always in my memory. So let us not use it right now. So let us follow what you said. So here I copy and paste the first two parts, these two, And then, as you told, I distribute this here. So let us see if it works or not. So it becomes P or R and P or Q. Okay?
Now I would use the conditional.
The conditional, but for the last arrow left. Okay, so what should I do? I will write negation of the box, which will be not R. What then? Or the whole combination. Are you with me? Yes. Then what?
Then you distribute again.
Distribute what over what?
Negation of R over.
Over the whole thing. You know, I don't care what this name is. This is one preposition. This is another preposition. They have the conjunction between them, but they all have also a disjunction outside. So I can distribute the disjunction over the conjunction. Yes? So what will happen here? So this becomes not R. Help me to write it.
P or.
Not R what? Or
P.
P
Or R.
or R in a pair of brackets, another bigger pair of brackets,
And
and okay, help me.
not R.
Not R or
P.
P
Or Q.
or Q. So far, so good. Okay, but there is no distribution involved here, neither there, because all of them are disjunctions. Okay, but what is your purpose? What is your suggestion here?
So on the left side, because of associativity.
Grouping, yes, yeah. Associativity allows me to remove the pairs of brackets without ambiguity, and commutativity allows me to reorder them. So what I will do, I will continue here. So which one? I would write it as my negation of R, what? Or R, or P, and then, so can I go back and write this as a conditional?
Yeah.
Yes, because of this law, you know. You can compare the right-hand side with this right-hand side. R is playing the role of the box. P or Q is playing the role of the circle. So instead of this one, I can write a conditional, but I have a conjunction there. So what can I write for this one?
R then P.
If R then PQ, yes? But what happens here? It's a tautology, and I have a tautology or P, which is a tautology, and that guy. And then tautology is the identity of conjunction, so it doesn't have any role there. So I can just get rid of it. So it becomes if R then P or Q. Yes, and that is exactly equal to the right hand side. Yeah, so that's also good. So I think it's good to know about them, but it's not hard. So I just want you to know the rules. So the next thing, that's nothing, and that is substitution. And substitution, we already actually use that without just mentioning it. So if you have a prepositional sentence, okay, and inside the, for example, if you have a prepositional sentence and then one of the components is P, and you know that P is equivalent to Q, you can go there and replace every appearance of P with its equivalent. Yes? It becomes a new preposition, but these prepositions will also be equivalent. So if I replace a preposition in a prepositional sentence with its equivalent everywhere, then I will come up with a new preposition which is equivalent to the previous preposition. So that's the substitution rule that we are going to use. And that is exactly the content of here. So if a prepositional component appears in a logic law and we replace all occurrences of this component with a prepositional sentence, then we will obtain another logic law. In addition, let alpha and beta be prepositional sentences that are logically equivalent, that is, alpha is equivalent to beta. If alpha appears in a given prepositional sentence theta and we replace occurrences of alpha and theta with beta, then the resulting new sentence will be logically equivalent of theta. Yes? So this means that all the laws that we learned for atomic prepositions are also valid for prepositional sentences. So the negation of a prepositional sentence, regardless of if it is atomic or a compound one, is equivalent to the prepositional sentence itself. So I have rewritten all of those laws, but instead of having them for atomic prepositions, I have written them for what? For prepositional sentences which are not atomic. So that's nothing. I will end this lesson by a nice example here. This is an important example. So I hope that you understand what I mean here. So I have given you 3 atomic propositions, P, Q, and R, and you see that I have arranged them as usual: 4 T's, 4 F's, 2 T's, 2 F's, and TF, TF. And then I have randomly distributed my T's and F's on the last column. I am asking you, can you tell me a preposition, a compound preposition, whose truth table is this? I don't want you to just solve this problem. I want you to think algorithmically. So the problem is this. It's a deep problem. So do you think that when I give you the last column in any way that I like to, you can come up with a preposition whose truth table is exactly what I just introduced? It's a deep question. Yes? It's a deeper question than just randomly draw them, okay? So here I have put these T's and F's randomly, if I remember. Yes? But these are organized as usual. So these T's and F's are randomly. My question is that, can I come up with a compound statement using P, Q, and R so that if I give you that compound statement, you can come up with, when you draw the table, it becomes exactly what I randomly wrote here. It is a deep question, but the solution is actually very simple.
I think yes, probably.
Yeah, so it means that, for example, yeah, okay, but can you come up with an algorithm here? Okay, I will give you a little bit of time to think. I write it here down.
But for this one specifically, or for every case in general?
What?
For every random assortment of them, like an algorithm for if you put any.
Yes, I will intuitively tell you the algorithm, but I want you to think about it a little bit. Only for this one, because if you come up with the algorithm for this one, you already come up with the algorithm for every case.
Yeah.
Yes. So let me. Yeah, you think. I will write it down here. Then we think about, and then we finish this lesson today. Okay. Any ideas?
I'm just thinking about.
Concentrate on the ones which are true.
Yeah.
Here I have 3 cases. Okay, what next?
So
for this question mark, I start with some. I would write this. I would write P and Q and R. Do you know what I'm going to do now?
Should be equivalent.
No, it's not finished yet. This is one part of the answer.
Imply or arrow.
No, arrow is a hard one to think about.
Okay.
Yes.
That's close. Because I was thinking about like the necessary condition for.
So let me think in this way. So the question mark is equivalent. One way to write it down. I just want to tell you that there is always one case, and I want to justify that this will work all the time. So I concentrate on the T ones. Okay. Of course, if all of them are F, then what do I write for question mark? Contradiction. So if all of them are F's, I don't have any problem to answer the question mark. The question mark is a contradiction. Okay. But if the question mark if I have at least one t in the last column, I concentrate only on the t's. And then I look here. T appears here. I write P and Q and R. All of them are T. So I write it as P and Q and R. But then I write OR. Okay, can you tell me what will I write? Because if you tell me the next, then everything becomes clear. Concentrate on the second T. So the second T is TFT. Because I want to have this OR, okay, what do you think I will write here? I would write P because P is still true, and I will make Q true by writing not Q, and I would write what? R. Okay, let us write and then check it out. Okay, can you guess what I will write next?
For the last T, that's going to be.
So what should I put here? Or
Not P.
And then I concentrate here, which is not P and Q and R. So it becomes not P and Q and R. Okay? So here I am guaranteeing that these T's occur. But the problem is that, are you convinced that F's will also occur in this way? Because that's important, yes? Because you know, I intentionally did it in a way that this one is true for the first assignment. Do I need to be worried about these assignments? What happens? No, because that's a disjunction. As far as I know that this is true, I don't even bother to look at them. So for the first assignment, TTT, definitely the first one is true, so ignore the rest. It will be true. Let us go to the next T. For the next T, the way that I constructed it, it is guaranteed that the middle one is true, so I don't even bother about this. The last result will be T. And for the last T, this one will be true, yes? So it means regardless of that. So the true ones definitely work. If you don't believe, you can check it in detail, but this is the way we think about it. But do you agree with me, this sentence will also produce the correct F's? Why is that? For example, why do you think that this will give this F correctly?
Because R is false.
Because we have TTF. When I have TTF, this conjunction cannot be true. Because this conjunction is true if and only if P, Q, and R are simultaneously true.
Yeah.
This conjunction is only true if P is true, Q is false, and R is true. So that's exactly why I want you to feel that this will definitely generate this F correctly. Yes? Is that understandable? So this is the algorithm. Could you understand the algorithm? So you concentrate on the T's and then use and not to write the conjunctions which are true based on that on the assignment of that particular row, and then use disjunction to combine them. Yes, so that's the whole story. And that was a good question actually. So it doesn't matter if you just randomly write anything, you can construct a compound preposition which gives you what you need. And this is something interesting. I mean, for me, when I saw it for the first time, it was a little bit shockingly hard. But I mean that when you think about it, it's not hard at all. But that's a very deep question. So if you want to have a random distributions of T's and F's, if you need, you can always construct. And in this construction, the connectives and negation and or is only used. Yes? Is that clear what I'm doing? Yes or no? For example, let me ask you this. Of course, you can immediately guess. PQ question mark. So this is TT FF, and this one is TF TF. Okay. So let me write this TF TT. You already know the answer by heart, hopefully. What's the question mark? It's a conditional. Yes? But let us use this algorithm now. If I want to use that algorithm, I should concentrate on where? These t's.
Yeah.
So for the first one, what do I write? These are t's, so it becomes p and q. Or this one, not p and q. So this one and not q. So that's the answer. Of course, you can see that is not a very nice answer because you already know the answer is what? P and q. But what is the answer? It's not p or q by conditional law. But then the question is that, is it really this one or not? Yes? How can I do that? I can factor not p out here. So if I factor not p out, what happens? It becomes q or not q. Do you agree?
Yeah.
But q or not q is a tautology. Tautology with this one is just not p. So it is not p and this one. So not p or p and q. But then it becomes again a distribution law. So it becomes what? Not p or p, which is a tautology. Not p or p is a tautology, so I don't need to write it down. So it becomes equivalent to not p or q. And not p or q is a condition. So this is a very nice algorithm. So this is good to know that it doesn't matter if you have a random distribution of t's and f's. And you always can construct a compound proposition that will give you exactly what you need. Okay, any questions? Understandable? Okay, so we stop here. We have to continue some sessions with logic. Still, there are many things we need really to go to the next topic, set theory. But yeah, we have to be patient a little bit. So I will check my schedule and I will announce it on Google Classroom or whenever you can come. Okay, any questions? Thank you.